So we are starting out with tension member design. So we're going to talk about limit states. This is going to be the theory, and then we'll have another lecture on how we implement that theory into actual design. So here are some examples of tension members. We've got, right, they're in trusses. You'll find some tension members, some compression members, and some tension members. The stays in a cable stay bridge, the suspenders holding up the deck of a suspension bridge. In a braced frame, if you'll recall when a lateral, right, if we have like a lateral force on a building, then one brace will be in compression and one brace will be in tension. Tension members can be anything if you want, right? Could be an angle, double angle, a T, a channel, W section, or you can build up a section. So these are just some examples of tension members. So limit states. Remember, limit states are a state at which a member is no longer performing the function that it needs. So there are two limit states, limits that a member will reach in which it is no longer performing its function. Two limit states associated with tension, specifically gross member tension. There's another limit state that we're going to talk about at the end having to do with connections, but there is yielding, and when we're talking about yielding, we mean excessive yielding. If you recall from our stress strain, right? We have our elastic portion and then a plastic portion. So if we're somewhere out here, we don't get enough strength, but it's going to be yielding a whole heck of a lot, right? So we get a lot of deformation with barely any additional applied load. So we have excessive yielding and we have rupture. That is when the member fractures or breaks. There actually is a third one. I'll write it here. It's called block shear, and it is a failure at a connection in tension. So two are associated with tension members by themselves. The last one is failure at a connection that has a member in tension. So when I'm talking about yielding on a gross area, right? I just drew this a second ago, but I apply a load, a tensile load, right, to a member. It elongates. Pick a prettier color. Right? It elongates some amount delta, and I can create this chart where I have my deflection, my elongation on the x-axis and applied tensile load on the y-axis. And it's comparable to a stress strain curve, right? We have some point at which it's behaving elastically, right? This is the elastic portion. And then this is perfectly plastic, right? Once it hits yield, it can't take any more stress or force. It just keeps elongating, just keeps deforming. And that happens when you hit, right, your yield stress, which is called Fy in steel design. So let's consider a 100-inch long tension member. Okay? And we're going to follow this stress strain curve. If I want to first look at my yield strain, which occurs when I hit yield stress, the elongation associated with that, right? If E equals delta L over L, then delta L at yield is equal to EY times my length. So 0.0015 times 100 inches is 0.15 inches. So it only has to elongate 0.15 inches to hit yield. Now let's look at, this is called strain hardening. Let's see. Right, this is yield. calculate, okay, I did this right. Calculate the deflection at the following points, right? I should have looked ahead. Right, let's. Try to see if I can move it. Yeah, there we go. So if I look at strain hardening, I've got ESA, my strain associated with strain hardening is 0.002. My strain, my change in length associated with that is 0.002 times 100 inches, 2 inches, or no, 0.2, right? Oh wait, hold on. 0.02, not 0.002. So just this tiny little bit right here, right, you go from 0.15 inches to 2 inches. So if I want to go out to my ultimate, right, I want you to calculate, take a moment, calculate ultimate, which is peak load. And rupture when it actually fractures. So go ahead, do a quick little math, right? Calculate those, I'll give you a minute. Okay, so hopefully you've figured this out. Ultimate or peak. The elongation, let's see, the strain associated with that was 0.15, so let's see. Change in length associated with that should be 15 inches. And if I look at rupture, should get you 25 inches. So that means, what does that all mean, right? This is excessive deformation, which is failure for if I, let's see, 0.15, if I just hit yield, peak, we got what, 15 inches? Rupture is 25 inches. So this means my member in tension might not break until I've applied 25 inches of this. It's displaced, it's elongated 25 inches, which is, I would consider that excessive, right? So it's failing. So when we look at yielding as a limit state, we actually just choose the yield stress because, right, that's only 0.15 inches. That's not a lot. 2 inches might be a little bit too much deformation. And defining these is not, these can vary a lot. These specific strain hardening onset, peak, and rupture, right? Strain hardening and peak can vary a lot, so it's easy to just go back and pick yield stress. So I'd say this is excessive. Right, these two. What am I trying to do? These two, right, they're pretty excessive. So we use our yield stress to control our design. For our yielding limit state. So that's our first limit state, talking about yielding and why we chose, I didn't do it, why the AISC chose yielding, the yield stress to control the limit state, as a yield limit state, and called it yielding. So our next limit state is rupture. Now, rupture was yielding. We talked about yielding on the gross cross-sectional area. Rupture, on the other hand, is over an effective area, because if you think about it, at connections, there's going to be holes punched in them for bolts, and that's going to reduce the cross-sectional area of the member that's in tension, right? Say we have, maybe I should have drawn like a tension member, right? We have a tension member. It has a force on it, and that force is over this cross-sectional area. Now, if I punch some holes in it for my bolts, I've now reduced that cross-sectional area. So there's less area to resist that tensile force. So a couple things to know. Holes, bolt holes are larger than the bolt diameter. We'll talk about why that is, or how you can determine that. And also, this is for calculating net effective area. You have to take out the hole itself, which is bigger than the actual bolt, and you have to add a little bit more because punching the holes can damage the steel around where you punched it, so it might not be usable steel near where you punched the hole. So let's look at a plate that is connected to another plate or a member thing by these 6 bolts. And in design typically uses average stress values, which assumes that there's a lot of ductility, right? We just saw how if you're looking at the length of 100 inches, then to go from onset of yield to full rupture had a deformation of almost 25 inches. So that's all the ductility. That's the wonderfulness of steel is the ductility. But if you're looking at a connection where you've reduced your cross section for a little bit, you don't get the benefit of that ductility. And we're going to go through a little showcase of how that happens. So initially, all right, we like to pretend there's an average, but initially, their stress concentrations exist near the bolt holes. So even though we like to pretend that the stress is averaged out and is even across the entire cross section, really it's got this little peak near the bolt holes. This is my stresses. That means if there's stress concentrations, the steel near the bolt holes are going to yield first. Now eventually, the rest of the steel will catch up, right? 1, 2, 3. Let's see, 1. Let's see, it reaches yield. And then, right, the entire cross section is in the same. So that ductility, that long, our stress strain curve, that long strain from onset of yielding to rupture allows the rest of the cross section away from the bolt holes to catch up. So the ductility is going to help you. However, asterisk, right? So that's why we get to use our average stresses, because that ductility allows everything to catch up. But how long does it take for it to catch up? Is the question. So let's look at right. Similarly, bolts and surrounding material will yield prior to rupture. So we assume each bolt transfers equal force. So each bolt transfers. There's 6 bolts, so P over 6. Right, P over 6 for 6 bolts. The plate will fail at the line with the highest bolt force. And we assume each bolt line, right, 1, 2, 3 line, transfers a third of the force, right, 2 times P over 6, so P over 3. P N, I guess. So let's do a little bit of free body diagrams, right? If I'm going from where I'm applying my load, P over N, I'm going to remind myself so I've got the entire, right when I'm coming to this bolt line, this first bolt line right here, I've got a force of Pn. That's the tensile force that's being applied to the member. And counteracting it is Pn over 6 and Pn over 6. So Pn over 3. So that means if I get to here, PN acting this way to the left, minus PN over 3 acting the other way. If I get to here, the force in the plate is 2/3 PN. Now acting this way at bolt line 2 is PN over 3. So if I look at the plate here, 2/3 PN minus PN over 3, now PN over 3 is the force in the plate. Right? And now acting on the bolt line, I have PN over 3, PN over 3 acting to the right, to the left in the plate, plus PN over 3 acting to the right in the bolt line. I have no force in the plate after bolt line 3. So right before bolt line 1, my force in my plate is PN. Between bolt lines 1 and 2, my force in my plate is 2/3 PN. Between bolt lines 2 and 3, my force in my plate is just PN over 3, and after bolt line 3, there's no force in my plate. That's good, right? There's no force in there. It's all being transferred by that bolt line to the connecting member. I did do it. Oh gosh. Right. I thought I need to look at what I'm doing. Right. PN over 3. So now here, right, is PN, and this is one-third PN, so here is just 2/3 PN, right? Next one, if this is PN over 3, right, then this has to be PN over 3, is acting in that part of the plate right there. So all this to say, where do you think then this is at the end of it, right? There's no force after bolt line 3. So all that to say, my force in my plate here is PN. The force in the plate before bolt line 2 is 2/3 PN, 1/3 PN. So bolt line 1 has to resist PN. bolt line 2 has to resist 2/3 PM. Bolt line 3 only resists 1/3 PM. This is the force in the plate. So, which bolt line do you think will fail? The plate at which bolt line do you think will fail? If you answered bolt line 1, you are correct. Because it has to resist the highest force. So that's just the physics way of explaining why the first bolt line fails first, because it has to resist the highest load. Unless there's something screwy going on, and then, yeah, unless there's a manufacturing issue. So, let's talk about how this is affected by stress strain. We did yielding on the gross cross-sectional area, way out here. Let's look at what happens when we reduce our cross-sectional area over the length of an inch, right? If it's a bolt hole. If we're looking at a cross section, we have bolt holes here. So the only material resisting the tensile force is what I've shaded in blue. And it has a length of 1 inch. We're looking at, a length in the direction of 1 inch. So now we talked about 100 inches. What if I have to calculate the strain? I have the same stress strain curve. Now instead of calculating it over 100 inches, let's calculate it over a length of just that 1 inch, where I have the reduced cross section. So go ahead and calculate what we did before, right? This was yield. Are those the same colors? Blue, green, red, orange. Right. So go ahead and calculate the elongation associated with these for inches. Hopefully you don't even have to get out your calculator to do all this. Strain hardening is 0.02, so strain hardening is 0.02 inches. The peak was 0.15, so the ultimate at the peak is 0.15 inches. And that was 0.25 inches, right? So let's go back and add those to our, let's go back and add those to the stress strain, right? 0.25 inches, so 1/4 of an inch deformation to get to rupture. 0.15 inches is my peak. Onset of strain hardening happens at 0.02 inches. And yielding happens at 0.0015 inches. So what is this telling me? Now when I looked at yielding over a long tension member, 100-inch long member, it was going to take 25 inches of deformation for it to even rupture. Now if I'm looking over a shorter distance, just the distance where I've punched some holes and put in a bolt, it only has to deform 0.25 inches. The difference from yielding to rupture has decreased, right, 100 times. So there's not much difference from the onset of yielding to rupture. I mean, 1/4 of an inch, right? You know, I don't know how much that is. It's like my fingernail or something. So that is why when we're talking about rupture, we talk about the effective net area because it's over a small distance. We've reduced our cross section over a small distance. And there's really not a lot of ductility, right? Going from 0.0015 to 0.25 inches. That's not a ton of ductility compared to yielding over a 100-inch long member where it deforms 25 inches before it. We don't want to have that 25-inch deformation, but here it could happen really quickly. There's not a lot of room for ductility. So that is why the rupture limit state uses FU and our effective net area. I'll tell you what effective means in a minute, but the net meaning you're taking out the holes. Right, you're reducing your cross-sectional area because you're reducing how much area you account to resist the load because you've reduced the cross-sectional area. So if we're talking about our two tension member limit states of yielding and rupture. Yielding occurs along the length of the member, out here somewhere. So it uses the gross cross-sectional area. And rupture occurs at our lead bolts, that first set of bolt holes, over our effective area, or net area. So rupture happens over a net area where you've reduced your cross section by punching holes in it. Yielding occurs somewhere along the length of the member, so we get to use our gross cross-sectional area to calculate our yielding limit state. One more thing to talk about before we pause. What if our holes are not in a line perpendicular to the load, right? What if they're staggered? Well, if we look right this length, let's draw these up better. This length right here, hope nobody's red-green colorblind. Right? This length is longer than if they were not staggered. Right? If they were just like that. Right? The hypotenuse is longer than the vertical distance. So if I have longer, I can hopefully get some additional strength. Right? Longer means more material before it fractures. So, but I do have to say, my additional strength, depends on how much it increases, right? How much that diagonal is longer than if it was straight. And now, right, if you look at that fracture, right, if this is my fracture, my fracture line, it's going to have to fracture along a diagonal, but my load is not perpendicular to it, but it's at an angle to it. So I need to break it up into components. Need to break it up into components. One that is perpendicular and one that is parallel. So you'll have a tensile component and you'll have a shear component along that fracture line. right? It's not in pure tension. If it was here, right, that's pure tension. That's pure tension. Here, it's tension and shear. So I do get some additional strength because it's longer. However, it is a kind of hard to calculate, which is why they did a bunch of research and they came up with design equations that we'll talk about in the next lecture. But just to let you know that that's what happens when there is a staggered hole as opposed to holes that are all lined up. All right, gonna pause right there.